Hi, this is Lab 5 for Physics 2211, and we'll be looking at how total energy correlates with the work done on an object. In this system, we'll be actually looking at a system that has rotational energy, and that'll touch on our first physics property, which is the fact that kinetic energy has two parts. Translational component, which is 1/2 times mass times velocity squared, and the rotational component, which is the 1/2 times moment of inertia of the object times the angular velocity squared. Another principle that we'll be looking at is the fact that energy is conserved in a system until an outside force interacts with it, so total energy will be equaling kinetic energy plus gravitational energy, and the work done will equal the actual total change in energy. This principle is used in many safety and standards professions as they will need to know the total or the approximate total energy in the system and how much force they can enact on the object to safely return the object. So in safety nets, they'll be doing that just as that. They approximate the total energy in which a human is falling, and they also know the approximate force in which a human can endure before they're injured, and that way they can calculate the amount of distance that the net can expand so that the human is safe. And this actually lab will be correlating more towards baseball glove designers, as they need to take in the total energy of the ball, and they have to find the total amount of force that their glove can withstand without breaking. In this experiment, we'll actually be looking at how much force a chair will take out on the football in order to make sure that the football stops its motion. We'll be using the change in energy formula, and the givens of the system is that the mass of the football is 407 grams, the gravity acceleration is 9.8 meters per second squared, the starting height of the football is 1.907 meters, the height of the chair is 0.430 meters, and the moment of inertia of the football, which we found in a study online, was 0.002829 kilograms times meters squared. Getting into the actual observations of the lab, here we have the video which we use Tracker on to track the center of mass throughout the flight of the football. In that video, we actually observed that the time passed before the football contacted the chair was 0.933 seconds. The amount of times that the football revolved was 3.75 times, which we looked at the laces for. The distance of the chair compressing from the time the football initially touched it to the time that the football actually stopped its motion was 0.06788 meters, and the starting velocity of the football was 7.344 meters per second. Using these observations and the givens we have before, we can actually calculate the force through a couple calculations. So first, we found the rotational velocity of the ball, and we used the formula of 2 pi times the revolutions divided by the time, and we found that to be 25.254 radians per second. We used the change of energy formula, and since the ball actually came to rest at the end, we only needed the initial kinetic energy for the change in kinetic energy. So we found that to be 11.394 joules using the two formulas we talked about earlier. For the change in the gravitational energy, we used mass times gravity times the change in the height of the ball, and we found that to be 5.9918, adding those up together to get the change in energy to be 17.386 joules. Then, using the fact that change in energy will equal the work of the chair, we set up the work of chair to be the force of the chair times the distance of compression, and when we divided the change in energy by the distance of compression, we can find the force of the chair, which we found to be 256.126 newtons. Using these same formulas that we had for the calculations, we can actually construct a model in our glow script. So here we are in the code for the system. We have the mass of the ball, the gravitational acceleration, the initial velocity and position of the ball, the moment of inertia of the ball, and the angular velocity. Here we inserted the kinetic energy formulas. So we have the translational kinetic energy right here, the rotational kinetic energy underneath. Using the formulas we had, using the formulas that we use for the calculations, we can actually construct a model in our glow script. So here we are in the code with the basics of the system: mass, gravitational acceleration, the initial position and velocity of the ball, the moment of inertia for the ball, and the angular velocity for the ball. Here we have the kinetic energy formulas with the translational energy on top, rotational energy right below that, and the fact that kinetic energy equals the addition of them both together. Then we have the gravitational energy right below that, and the total energy of the system equaling the kinetic energy plus the gravitational energy. These energies are actually updated throughout the simulation and then plotted onto a graph, which we will come in handy later. And at the end of the simulation, it'll actually print out its force for the chair by dividing the total energy by the distance of compression that we saw in the video. So when we run this program, we'll find that the ball actually travels in a very similar flight path as the observed video that we had. Going on down to the energy graph, we can see that the kinetic energy and the gravitational energy are pretty much inverses of each other, and that the total change in energy hovers around 0 for the whole entire simulation, because it is a closed system and total energy is conserved until the chair enacts its force, and that's when we see the change in energy jump up to 18.6 joules, and the model actually calculated the force of the chair to be 277.882 newtons. And then using that, we can actually go into the discrepancies as why our model had 277 newtons and our actual observed calculations calculated the force to be 256 newtons, and this is there's a couple reasons why. So the ball was tilted upwards. It already had air resistance, but this in fact increased the amount of air resistance that would have enacted on the football throughout its flight. And this pretty much just means that the system is not closed at all, because the air resistance is affecting the amount of energy in the system as it loses energy throughout the flight path, which is why our model is a lot larger for the force by the chair than our observations. The amount of rotations was estimated based on the laces throughout the video. We couldn't accurately see it, so we guessed that it was 3.75 based on the laces position, but that wasn't the most accurate thing in the world, and that could affect the kinetic energy totals, which could in turn affect the force of the chair. And the starting frame actually may or may not have had the finger still touching the ball. I just couldn't see it clearly in the video, which could in fact mess up the initial velocity and in turn affect the final force of the chair we saw in the observation. So that's probably why the model was over predicting a lot. But as we go into the lab, it doesn't really affect what the lab actually meant. In this lab, I was really trying to focus on rotational energy and its importance, and I do believe that rotational energy makes a big difference in systems, because if you were to take it out in this system, even though it's only providing 0.9 joules, which is a very small amount compared to its translational component, it actually decreased the amount of force that the chair enacts by 13.3 newtons, which is a lot of force. And plus, in other systems in the world, rotational energy may be the major component of kinetic energy, like in dreidels. It'll rotate a lot faster than it'll move side to side, and therefore it's something that you can't ignore in all systems, especially if you're in those professions that we mentioned earlier. It will affect a lot the forces that you can use for the safety of people or objects and everything. And here we are with the citations for the moment of inertia for our football.